Okay, so empirical formulas are basically the simplest, oops. Sorry about that, I dropped my mouse. So it's the simplest whole number ratio of the atoms that are in a compound. Okay, so just hold on a second, I'll actually give you an example of that. So the molecular formula is the actual number of atoms that are in that particular compound. Okay, so if we look down here, we have benzene. So the molecular formula for benzene is C6H6. The empirical formula for benzene is CH. So you see the difference? So you want it the simplest form, right? So basically you divide it till you can't divide it anymore and keep a whole number. So the molecular formula for acetic acid is C2H4O2. The empirical formula of acetic acid is CH2O. Coffee hasn't hit my stream yet. We're working on it. Although I did start off with a cup, it still just hasn't kicked in. So do you guys see that? Simple?
Yes.
Yeah, it's simple.
Okay, good. So let's give it a test run. So if we have C6, H12, O6, what would be the empirical formula?
CH6O.
CH6O? Are you sure? I'm going to write that down.
It would
Oh,
be
two, H2.
Yeah, H2, 0.
Okay.
Oh.
Okay, piece of cake? Yeah, no?
Yeah.
Good. Okay, so here's a benzene ring so you guys can get an idea of what a benzene ring looks like. So a benzene ring has a carbon in a ring, 6 carbons in a ring, double bonds alternating between the two. These lines here, one line means a single bond, 2 lines mean a double bond. If there's 3 lines, it's a triple bond. Okay, so let's see. So this is acetic acid or vinegar, which we kind of know it as. You guys will play a lot with vinegar in your take-home kits. So in this case, our acetic acid, you can see the chemical structure here. And when we get the empirical formula, right, we're getting rid of those carbons. And so we won't really draw the empirical formula. The empirical formula is just kind of used as means of a determinant, right? So often we'll use an instrument to sit there and get an idea of what that chemical is. And so once we get the empirical formula, because the instrument that we're looking at, it compares ratios. It's not going to compare the actual structure or how many carbons you actually have in a lot of the instrumentations that we use. It will compare ratios of carbons to hydrogens to oxygens. And so at the end, if you're comparing those ratios, you can get an idea of what the empirical formula is. And then you can start trying to figure out what the chemical compound is. And we'll do that here in a second, okay? So, but before we start about more on empirical formulas, let's talk about isomers. Okay, so an isomer is a compounds, or they're compounds that have the same chemical formula, but they have different molecular structures. Okay, so you know how we've been drawing or writing the chemical formula C6H12O6? Yes?
Yeah.
Okay, so This guy could actually be glucose. It could be fructose. It could be galactose. It could be galactose. It could be arabinose. So it could be any of these forms of sugars. So these sugars are going to differ from each other by their structure, right? So for instance, glucose is a six-ring carbon chain. Put my O here. 1, 2, 3, 4. Okay, each of these vertices represents one of those carbons. So that's 1, 2, 3, 4, 5, 6 carbons. And then here's our oxygens, 1, 2, 3, 4, 5, 6 oxygens. And then each of these carbons will also have hydrogens hanging on to them because carbon can have 4 bonds. We'll talk about that a little bit later. So technically there's other hydrogens here, so that would count for all of the other hydrogens. Fructose is a 5-ring structure. Okay, so structurally, they're different. Chemically, I mean, their chemical formula is going to be exactly the same. Do you guys kind of see that?
Yep.
Okay, so here's another example of an isomer. So here we have acetic acid and we have methyl formate. Their chemical formula, exactly the same. But structurally, are they different?
Yes.
Okay, where's the difference? Can you circle it on my screen?
Oh, are they actually different? Yeah.
Yeah, the fact that we have that oxygen in between the 2 carbons,
Mhm,
and then here the oxygen is on the outside of the carbons.
mhm.
Okay. Good job. Okay, so here's another example. So this is called a steric isomer. So one has a plus orientation and one has what we call a minus orientation. These are considered differently because they're going to behave differently. Okay, so carvelin, so carvelin plus or plus carvelin if you look at the orientation, they're kind of mirror images of each other, right? In the old days, they used to use the S and the R orientation. Like S was like sinister, and then R was like normal or the equivalent. Sinister meaning they thought of it as being bad, right? So they're actual mirror images of each other, and so they actually will behave differently as a result of that. And so if you look at them structurally, they look exactly the same, but they're just a mirror image of each other. And we'll get more into that once we start talking about organic chemistry in the second semester. Okay, so one is basically found in some grain, and then the other one is actually found in mint. And so, does your grain smell like mint?
No.
I should also say
No.
the mint smell that you get is a result of that chemical. So, okay, so you guys are already familiar with the periodic table, so we don't need to go over it too much, right? Generally, right? Because we kind of talked about it. We've been beating it in. Yeah, no, maybe.
Yeah.
But we'll talk about a little bit though, right? So for instance, the periodic table basically was, it was founded by these guys, and they kind of had this organization in their own heads. And so we've made adjustments to that over time because we start realizing the number of protons and the number of electrons and the number of neutrons. And so we're able to sit there and order them in a certain way, right? And so, but what they found is that when they were looking at things, they found metals that had the same properties, right? So they had like lithium, sodium, and potassium. They were all shiny. They all conducted heat really well. They also conducted electricity. And so these guys have very similar properties, right? And if we take a look at our periodic table, of course I had to close it. No, I didn't. Good. So if we take a look at our periodic table, these guys are right underneath each other. So we organize these so that they fall directly underneath each other, right? Because they have properties that are very similar to each other, okay? So in the case of calcium, strontium, barium, these guys are also metals. I mean, they're also shiny. They also have, they conduct heat and electricity really well, but they're not as reactive as your lithium, sodium, and potassium. I should probably tell you that. So if you stick lithium in the air for a while, it'll actually ignite. It'll catch on fire, right? Or sodium or potassium, like the metals completely. Or if you put them in water, you start getting steams and sparks coming out, right? So in all three of those cases, they're very reactive, right? And part of their reactivity is a result of them not having that stability, right? So did we talk about the noble gases?
I believe so one time, but very briefly, I believe.
So we have the noble gases, right? And I think I kind of asked you guys about what does nobility mean to you? These are the noble gases. These guys are like stable. They're really, really stable, okay? Now, since they're stable, the reason that they're stable has to do with their electrons. And we'll be talking about that in the next chapter a little bit more, but it has to do with their outer shell is completely full. So they're full, right? They're as wealthy as they can be. They're happy, you know, because they're wealthy. They don't have anything to worry about. They're perfect, right? They have everything that they need. Now, these guys, all of the other elements on the periodic table, right? They're looking to try to be like the noble gases. They want to get their outer shell filled like the noble gases. So that means that they want to get electrons or give electrons so that they have that stable outer shell, right? So some of them are too rich, some of them are too poor, right? So these metals, they have a couple of extra electrons. So this guy has one electron, let's say sodium, talk specifically about sodium. Sodium has one more electron than the noble gas neon, right? So because sodium is, has a little extra, right? It has that one extra electron. It's like, let me just give this away, right? So then I can be like neon. So because it's so anxious to give it away, to be like neon, it's going to be very reactive. Okay, so the further you're away from the noble gas, typically the less reactive you are. So sodium is more reactive than magnesium. Magnesium is more reactive than scandium. Okay, so if we go over here on this side, fluorine is one away from being like neon. Fluorine is the most reactive chemical on the periodic table. It is anxious. It wants that one electron. So excited. It's like, hey, need it, right? Okay, so it's going to try to find a way of getting that electron. And so the way that you get electrons, right, there's a couple of ways. You can take electrons. You can give. Well, so the way that you either get to your octet being full is either take, give, or share, right? So now let's think like thieves. I'm not saying that anybody here are thieves or have never been thieves, but if you were a thief, right? So would you steal from your neighbor, or would you steal from somebody who lives in another town?
Far away.
From your neighbor?
Another town far away.
Another town.
Okay, so obviously somebody's a really bad thief. If you're stealing from your neighbor, so they have a brand new bike, you take their bike, right? Aren't they gonna say, hey, that's my bike that just got stolen. Why did you steal my bike, right? Does that make sense?
Yeah.
Yeah.
I
So
just
it doesn't
figured
make
because they're closer.
you were thinking because they're closer, but it doesn't make sense, right?
Yeah.
Right? It makes no sense. So it makes more sense to steal from somebody from another town because the probability, you have a couple of probabilities working for you. One, they're in another town. Probability of them coming into your town is less likely. That's one thing. The other thing is they're in another town. Them coming over and recognizing you at the same point is very less likely, right? So it makes sense that you're going to take from somebody who's in a whole nother town, right? So if you look at it, these guys are nonmetals, right? So your nonmetals, these guys are going to want to take electrons because they're close to being the noble gases. So they want to be pulling electrons. And let me kind of explain it like this. So you want to think about it. If you're the individual and you don't like doing work, do any of you guys like doing work? If you didn't have to work, would you work? No, if I didn't have to work, I would sit on my ass and watch soap operas all day long and eat ice cream and maybe go work out just because I want to look good, right? But that's about it, okay? I'm just being honest, being truth, right? But we have to work, right? So you want to find a job that you're doing the least amount of work. That's part of the reason why you're going to college, because you know if you're in the fields, you're working your ass off, right? Just to make a little bit of money, right? Or if you're working at Tomotech. Oscar, are you working your ass off?
Yeah.
Yeah, it's a lot of work, right? Just to make that little bit of money where you can actually go and get your education, and then you can sit in a nice, cushy, air-conditioned lab, occasionally talk to people, and do a couple of experiments every once in a while, right? So the reason why you're here is because, in a sense, you want to do less work and make more money, right?
Yeah.
Okay. At least I hope that's why you guys are here, right? Or part of the reason, right? So, any of you guys independently wealthy? Let me know. I'm single. I could be married within a day. Okay, I'm just letting you know right now, okay? It don't matter. You could guy or girl. I'm open to everything. So, anyway, so the thing is that these guys, the closer you are to being a noble gas, the stronger you're going to be in most cases, okay? So you're going to want it that much stronger than the guy that's further away. So carbon here, carbon is located right there, okay? So if we count, that's 1, 2, 3, 4. It's 4 away from being a noble gas if it gains 4 electrons. So it would have to gain 4 electrons to kind of be like neon. Let me erase some of this so it doesn't look so crazy. Okay, so if we go the other way, it's 1, 2, 3, 4. So it's 4 away from being like helium. So carbon is kind of like, you know, well, I guess I could lose, but maybe I'll. So it's kind of iffy, right? So it's not going to be as hungry for it as, let's say, fluorine. Fluorine is like right there, needs 1. So what do you think fluorine's going to do in most cases? Is it going to not give it up? Is it going to try to get rid of 1, 2, 3, 4, 5, 6, 7 electrons? Or is it going to want to try to gain a single electron? Which one is easier?
Gain.
Gain, right? So it'd be easier for them to gain that 1 electron than it is to lose 7 electrons. So that's part of the reason why fluorine is like, hey, you better give me that damn electron or I'm going to break your leg, right? So it's really anxious. Or it's going to be, if it's on the same side of town, it's going to say, hey, let's share that electron and try to take it most of the time. Okay? Because it's so hungry for it, even if you're sharing, it's going to have a stronger pull than that person that isn't as hungry for it. Okay? So lithium, what do you think lithium is going to do? Is it going to want to gain an electron? Is it going to want to lose an electron?
Lose that electron?
Lose.
It's going to want to lose that electron, right? So it's going to be like, okay, let me just drop it off here. And if fluorine's around, fluorine is going to say, hey, bro, I'll take that. You know, you're giving it away. I'll take it, right? So then what would be the charge on lithium if it loses an electron?
2.
Positive +1. I mean, yeah.
So it'd be Li plus. That would be the charge. 1 plus, right? Because it lost an electron. What would be the charge on fluorine? If it takes that electron.
Negative?
Now, if they're in the same vicinity of each other, what do you think is going to happen? Think about when you were in high school and you're that good girl and the bad boy comes up to you, hey, baby, what's your name?
They're attracted to each other.
Ah, yeah, they're attracted to each other. So my lithium and my fluorine form what we call an ionic bond. 2 ions coming together, ionic bond. You get it?
Yep.
Okay. So this is an example of an ionic bond. Okay, now this is all based upon the fact that we know that these elements, they kind of want to be like noble gases. They want to be like the cool kid, right? And so they do what they can do to get like that. And then because they're doing that, because they're exchanging electrons, either they're sharing means that you're going to be making covalent bonds, but if you're taking and giving, you're going to be forming ionic bonds. Okay, so the fact that fluorine took the electron from lithium, right? That's an example of forming an ion. So you're going to make an ionic bond in it. Okay, you guys get that so far?
Yeah.
Okay, so now if you look at the periodic table, it's really organized, right? Let's see, clear. So if we scan over the metals here, this will help us. These are all of the metals that are on the periodic table. So these guys are all kind of shiny, right? They all conduct heat and electricity. But we know that these guys are a special group of metals. These are alkali metals. These alkali metals, you know, because alkali, I think of it when I just hear that word, it just kind of rubs me wrong, like somebody wants to fight me all the time, right? That's what alkali makes me think about. So these metals here, these metals, all these metals here are very reactive, right? So, and it's funny because as you go down, right, the reactivity changes a little bit. They become a little less reactive, right? But they're still reactive, okay? Now, these metals, alkaline metals, they're kind of a little more docile. You have that IN, that INE at the end, alkaline, right? Alkaline, I think of being as that IN kind of simmers it a little bit. So they're not as reactive as these guys. These guys here are your transitional metals. Now, your transitional metals aren't as reactive as your alkali metals or your alkaline metals, but they're a hot mess. And we'll get into why they're a hot mess in the upcoming chapters. So when they are forming their ions, like, and I'll talk to how we'll talk about their ions forming, they form their ions a little bit differently, and it's not always going to be exactly the same. So like, for instance, iron could have a +4 charge, iron could have a +2 charge, iron could have a +1 charge. It could also have a +3 charge. Okay, so depending on who it's going to interact with, the heat that you do it at, the time that you do it at, it's going to be very finicky. So it's a hot mess. It's in transition, going through those changes, the transition. Okay. So alkaline metals, they're always going to have a +2 charge when they form ions. Not to say that they have to form an ion, but under certain circumstances, when they're not in, let's say, when they're not just in air or anything like that. So typically they have to be in an inert material for them not to react. They're going to react slowly, not as fast as the ones that are in group 1. They're going to have a slow reaction going on in most cases, right? So you can sit them on the table and stuff like that and interact with them, and it'll take a couple of months before they actually start interacting with the air or with water. But they will interact, right? Or if you put heat in it, it'll cause it to interact faster. And we'll talk about that here in a second when we talked about reactivity series. Okay, so these metals, when they form ions, they're going to form a +2 ion, always. So they're always going to be +2. These metals are always going to be +1. Okay, so now I want you to use those skills from what we talked about so far. Why do you think these metals here, these alkaline metals, the ones in yellow, why do you think they're going to be +2 all the time when they form ions?
Is it because they're on the second column?
That's right. So how many electrons do they need to get rid of to be like a noble gas?
2.
2. Make sense? Okay. So why do you think these guys are always going to be +1?
Because they're on the first column?
They have 1
Okay.
electron.
So they only have 1 electron to get rid of, right? Okay. So these guys here in column, this is the 17th column. These guys are called halogens. So the halogens, they're 1 away from being a noble gas. So they're going to always want to get that 1 electron, right? So if they form an ion, what charge will they always have?
Negative.
Okay. Piece of cake?
Yes.
So this group here, they're 2 away from being a noble gas. What do you think is going to be the charge that they have?
2 negative.
-2.
That's right. Piece of cake?
Yes.
Yeah.
Okay. So you guys kind of seeing how they're organized? The periodic table is kind of organized? Yeah, no,
Yes.
maybe?
Yes.
Okay.
Yeah.
So the one thing that we can keep in mind is if you look up top, right? You have numbers that are associated with those columns. And if you look on the side, you have numbers associated with the rows. So the ones that are in the same column, right, they're going to behave very similarly in most cases. So for instance, all of the halogens are going to behave very similar to each other, right? And so sometimes, let's say you don't have one, you can kind of substitute for the other because basically they're going to react very similar than the other one will. Sometimes. Now, there are some circumstances that they will behave differently, but for the most part, you can say that they're going to behave very similarly. Okay? So the ones that are in this column, they're going to behave very similarly. Okay? So as we saw with the metals. Okay? So these guys, the numbers up top, this is called your group. The numbers on the side is called your period. Okay? So groups behave very similarly. Your periods, not so much, right? Okay? So things that are in the same period are not necessarily going to behave the same way. Okay?
Yes.
You guys get that? Okay, good. So we can keep going. Okay, so we've gotten organized in terms of the periodic table over time, but these guys made a big contribution to understand how to arrange it. And so if you take a look at it, this is how they initially had it arranged. And so we've made quite a few modifications over time. And so the modern periodic table is what we've basically been looking at. Okay, so elements can be classified in three major ways. They can be metals, they can be non-metals, and they can be metalloids. Metals, you guys know, are going to be shiny, malleable, good conductors of heat and electricity. You guys know what malleable means?
It's like easy to like kind of like a Play-Doh, like easy to move.
Yeah, so they can be movable and stuff like that. They're not brittle. They're not going to break easily, right? So we can kind of, if you have a thin sheet of metal, you can kind of wiggle it, you know, depending on the metal, of course, but it's not going to snap in half, you know, and so it has some ability to it. So we're non-metals. They're going to be dull in appearance. They're going to be poor conductors of heat and electricity. And then the ones that are going to be solid at room temperature, a lot of them non-metals are going to be gases. The ones that are going to be solid, they're going to be kind of brittle, right? So if you take a look at sulfur, right? You play with sulfur, you drop it on the ground, it splits in pieces, brittle, okay? Or phosphorus, same thing. Or carbon. If you guys play with charcoal, if you got a lump of coal for
Yes.
Christmas once, and then you got so mad and threw it across the room, you know? So, okay. So metalloids they have properties of both metals and non-metals. So they do conduct heat and electricity. They do it fairly well, not as good as metals do, but still fairly well, okay? And they have properties of both characteristics, okay? And so let's see. So these are your metalloids. Okay, so often a lot of people will mistake aluminum for a metalloid. Aluminum is a post-transitional metal. It's not a metalloid. Okay, so that's one of the reasons I also love P-table, so I can actually make sure I get it right. You know. Okay. Okay, so main groups. So initially, the first elements that were kind of characterized and that we kind of understood, right? We're group 1s, group 2, and from group 13 to group 18. So these guys, 1, 2, 13 through 18. They were kind of easy to understand. And because, you know, they kind of obeyed certain rules, right? We know that group 1 metals, right? They're always going to have what charge associated with them when they form ions?
+1 charge.
Positive. Yeah.
Okay. We know that group 17, non-metal, it's going to have what charge associated with it? I heard somebody say negative.
-1 charge.
A -1 charge, right? So they're kind of straightforward. They're not complicated, right? So these were called the main groups. And so on older periodic tables, right, what they would do, they would say, they would say 1A, 2A, and then they'd go immediately here, and then that would be 3B, 4B, 5B, 6B, 7B, and 8B, right? So that's the way that they used to arrange it in the old days, right? So now the modern, most periodic tables just do straight across groups because we understand a little bit more about the transitional metals, okay? And the inter-transitional metals, okay? Okay, so this just basically tells you that. And so often you'll say main group elements. Those are the ones that kind of obey this little standard rules that we have. And then transitional metals, they just kind of throw everything off, right? And so that's also your inner transitional metals do the same thing. Okay. So we've already talked about the different groups, and then these are the names that are going to be associated with those groups. Okay, so you be familiar with the names, okay? Recognize which groups they are. So this just shows you the order that I showed you on P-table. So don't you love P-table? Isn't it great? So you can just click on it and it has it all shown up for you.
Mm-hmm.
It's kind of like I'm selling it or something, right? I should have stock in P-table. Okay, so you guys understand the concept of ionic compounds, right? So an ionic compound, plus and minus charge coming together, right? A molecular compound, right? That's when they're sharing electrons. And so that's going to be when they have covalent bonds. So remember when we talked about, do you rob from your neighbors, right? So no, you don't rob from your neighbors, right? You get your neighbor who's a little bit weaker than you, right? So let's say we have oxygen and fluorine. You don't rob from them. You say, can I borrow your bike? And you keep it for a week and a half, right? And so, and they come back and they'll get it for a little bit. And then, so in that case, you're sharing, right? It doesn't have to be even sharing. It's just sharing. How many of you guys have siblings?
Yep.
Yep. Are you the oldest or youngest?
Oldest.
You're the oldest?
Middle.
Youngest.
So you can relate to me, right? So I'm the oldest of my siblings, right? And I come from a pretty poor family, right? So often what my parents would do, they would get us socks, underwears, and maybe a t-shirt or something like that for individually. And then we'd get one nice gift together for Christmas, right? So it'll be like a PlayStation or something like that, right? Back in the day, it wasn't a PlayStation, it was an Atari, okay? So what would happen is, what was that?
That's all right. It was cool though.
Oh yeah, it was. I don't complain, you know. You get what you get and you be happy with it, right? I learned that real quick because it could get taken away just as fast.
Amen.
So, as I said, my parents would get us one gift that we'd have to share, right? And so I'm the oldest. And at that time, I was probably stronger than both of my sisters. I have two sisters. There's points in the lifespan, and if you met my sisters, they were pretty strong. They got really strong real fast, right? Because they didn't like being bullied by me. So my philosophy was, I'm the oldest, I should get it for the majority of the time. So it would work out. My mom would go to work. So the whole time that my mom was at work, right, I would be playing the video game, right? Except for when I'm in school. So, and my dad was on the boat. So playing video games. As soon as my mom was getting ready to come home, probably like 5 minutes before, because she tried to be smart sometimes and come home a little bit early, try to catch me playing a video game and not sharing with my sisters. As soon as I give it up right before my mom got home every time. So we were sharing, right? Because she told me we had to share. Did I not share with my sisters?
Yeah. A little bit.
Was it even? Was it even sharing?
No.
No. So when we talk about
Definitely had
a
a
molecular compound, it has two ways of sharing. We can have it sharing where we're sharing evenly. So we're sharing those electrons evenly, or we could be sharing those electrons unevenly, where
You were
one gets it
sharing.
more than the other.
You were definitely ionically sharing.
Ionically sharing. So it's not ionically sharing because I didn't take, right? Ionic bonds or an ionic compound is that process of taking. I may have ionic characteristics, right? It seems like I'm taking, but it's not real, you know?
It was the weakest sharing.
Okay, so let's talk about these type of bonds. So we have water, H2O. Now, hydrogen has one electron, right, that it can share. And it's always going to have one electron. Hydrogen is going to want to be like helium. So it only wants to get one electron. It doesn't want more than one electron at all. So if it's going to share, it's only going to share that one electron. And it's only going to share the other one, right? Oxygen, how many electrons does oxygen need? To be like a noble gas.
These two.
2.
It needs 2. Okay, so hydrogen is going to share one electron, and oxygen is going to share one electron. Hydrogen is going to share one electron, and oxygen is going to share one electron. All of the other electrons, this is called the Lewis dot structure. All the other electrons are going to sit out here, right, on oxygen. It's not going to share those. It's only going to share one with this hydrogen and one with that hydrogen. Now, hydrogen is happy, right? It's happy as a clam because it's sharing that one electrons. It's really like helium. It's like, hey, I'm just like you, helium. I got the same number of electrons. I'm cool now, right? But it's sharing with hydrogen. Now, the thing is, oxygen is saying, yeah, I'm sharing as well too, but I need to make sure that I get the electron the majority of the time. So oxygen is kind of like I was. It's stronger, it's bigger, it takes it the majority of the time. So it spends more time, the electron spends more time over on the oxygen side than it does on the hydrogen side. And that's in both cases. So this guy, it forms what we call a dipole, right? So di meaning 2, pole meaning 2 poles, right? So in that case, this guy, instead of being totally neutral, right?
Fair.
It's going to have what we call a partial positive charge on this side, and this guy is going to have a partial negative charge, okay? And that's the same thing that's happening over here. Partial positive, partial negative. So this symbol here, this is a lowercase delta, right? Meaning change, right? And so we kind of use that to represent that partial charge because it's not a complete charge. You know, kind of like, you know, when we're talking about lithium fluoride, where this is a minus and the lithium, I was going to put another. And the lithium is a plus, right? Remember when we talked about that just a second ago?
Yes.
Yeah. So these guys are complete charges, okay? So this is complete positive, and this guy is complete negative. These guys are just, they're a little positive compared to these guys, and this is a little negative, you know? Do you guys kind of understand what I'm saying there?
Yeah.
Okay. Okay. So this is called polar. So this is a polar, and the term covalent means that they're sharing the electron bond. Okay, because they're polar, right? So that means that water, have you put water and salt together?
Yes.
Yes.
So what is the chemical formula for salt? Anybody?
Na.
The chemical formula for salt is just Na,
NaCl.
NaCl. Okay, so NaCl, sodium chloride, is just an ionic bond. You have a sodium that's going to be plus, and you're going to have a chlorine that's going to be minus. When they come together, that positive and negative cancel each other out, so we don't write the charges, right? So when we put this in water, what happens? What happens when you put salt in water? Do you see salt still at the bottom if you stir it in, and if you don't put too much salt?
No.
Now what happens?
It dissolves.
It dissolves. So one of the reasons it dissolves, the reason that it dissolves is because it's interacting with water molecule. Can you guys see my writing on the bottom?
Yes.
Okay, so this partial positive is going to interact with what?
The partial negative.
Is it partial negative? So it can interact with water, because only water is going to have a partial negative.
Mm.
If we're talking about salt, what is it going to do with the salt? Who's it going to interact with the salt? If that partial positive is going to interact with what?
The water, right?
So we're talking about the water molecule.
Mhm.
Who is it going to interact with? Of course it can interact with water, so it's going to interact with that other partial negative
H.
with another. So what's going to
Fine.
interact with H? If I have salt broken down, I have the chlorine and I have the sodium.
And the
Because doesn't it dissolve?
yes.
Okay, so if it dissolves, who's it going to interact with? Who's the partial positive or the H going to interact with? Is it going to interact with the chlorine or is it going to interact with the sodium?
The chlorine.
Why?
Because it is negative.
That's right. Because
Okay.
this guy is negative, it's going to get surrounded. Let's see if I can do this. Let's see if I can get fancy here. Nope. It's going to get surrounded by the water molecule. Where it's interacting with the H. So all of the H's are going to orient towards the chlorine and surround it. Since these guys are all partial charges, these are partially plus, they can't satisfy them by themselves. It takes a couple of them to sit there and surround it. Okay? Now, the sodiums. Who's the sodium ion going to interact with?
The oxygen.
The oxygen. So same thing's going to happen here. Oxygens are going to surround it. Now, ionic bonds can be separated. So water is kind of like a home wrecker, right? And it's playing with both of them. It goes to sodium, the sodium ion, and say, hey, baby, you don't need chlorine. You got me, right? And then it goes on the other side, goes to the chlorine ion. Hey, baby, you don't need sodium. You got me, right?
Oh, a player.
Right? So it breaks apart the ionic compounds. Okay? Because the fact that it's polar. It's a polar covalent molecule. Now, when you're sharing, you can't break those bonds. It takes a lot of energy to break those bonds, right? So if you're sharing the electrons, it takes a lot of energy. But if you're just interacting based upon charge, right? Water could come in there and just sweep you off your feet. And you're like, oh, I'm going to go with water. Water is fine, And they're both saying they're fine, Sodium is saying it's fine and chlorine is saying fine. So they're really anxious to kind of, oh yeah, we can separate, right? No big deal. Now, if we remove the water, what's going to happen? So we boil water off, right? Water gets all hot and bubbly, right? Got what it needs. What's going to happen? What happens when you boil water, salt water?
It'll evaporate.
Those of the salt remains.
Salt remains. So then the ions get back together. Water's gone, right? Water left us. Let's get back together, right? That positive and that negative come back together. Okay? You guys see that?
Yes.
Okay. So we've talked about ionic bonds. We've talked about covalent bonds. So this is an example of a polar covalent bond. Okay. So let's talk about a nonpolar bond. Remember when I talked to you guys about carbon? Carbon is in the middle. It's like, I can take electrons. Oh, I can give electrons.
I had a
What do you
question
want?
about
Right?
you erased it, but before I had a chance to ask, I don't know how the oxygen became the bigger brother. Like why did we determine that oxygen would be on top versus?
So why is it so much stronger than the other? So the reason why oxygen is so much stronger than the other, than hydrogen, right? Hydrogen is up a level, right? It doesn't have as much to work with, right? It doesn't have as much pull because it only has that one proton that it's working with. Where,
Okay, gotcha.
where oxygen has 8 protons. And so its pull is going to be more than the hydrogen.
So it's based off protons. Perfect.
Well, it's partially based off protons. There's a little bit more to it than that. It's location, where you're located at. It's also 2 away from being a noble gas. This guy is only 1 away from being a noble gas, but it only has to worry about that one proton to satisfy, right? So its pull isn't going to be as strong as the oxygen. So oxygen is going to have a stronger pull. Now, when you start getting bigger, so when you start getting too big, what happens is that you kind of lose track of the electrons towards the end. Your pull is not as strong because you've gotten too big. So oxygen is kind of like the right size. It's not too big, it doesn't have too many to worry about. And so it still has that strong pull on it. And so we'll start talking about that. You'll start noticing that as you get bigger, the weaker your pull is going to be because you've gotten so big. You have the center of the atom, and then you've just gotten bigger, right? And so, and I'll show you an example and kind of explain that to you a little bit more. But the best way of thinking of it, oxygen is kind of easy to satisfy. I'm sorry, not oxygen. Hydrogen is a little bit easy to satisfy because if you just give it that one little extra, it's like, okay, I'm going to be happy with it. It's not too demanding, where oxygen is a lot more demanding because it has more people to try to satisfy or more protons to try to satisfy. Okay, let's see. We're good on time. Is everything going cool? Pretty simple so far?
Yeah.
Yeah.
Okay. Okay, let's see. Oh, so we're talking about methane. So methane is different than water. So I told you about carbon kind of being in the middle, is kind of fluctuating. So it's not going to have a strong pull, right? And if you actually look at the pull, so we have what we call, and we will talk about this a little bit later, but we have electronegativity. Electronegativity is your desire to take electrons. Fluorine has a really strong desire to take an electron. Oxygen has a really strong desire to take an electron. The desire of hydrogen to take an electron and the desire of carbon to take an electron are about the same, right? They're really close together. So in this situation, you're not going to have a dipole forming. Plus, you also have 4 carbons. So it's kind of like if you have quadruplets, they're exactly the same. Neither of them are stronger than the other. If one is pulling you forward, one is pulling you to the side, one is pulling you to the other side, and one is pulling you in the back, right? Is any of them going to pull you more towards them than the other?
No.
So in that case, you're not going to form what we call a dipole in that situation. Nobody has a stronger pull than the other. So this is called a non-covalent bond because it isn't polar, right? So a non-polar bond, non-polar covalent bond. Okay, piece of cake?
Yes.
See, clear. Okay, so we've talked about who gains or loses electrons. Is that going to be in an ionic compound or is that going to be in a covalent compound?
The Nuggets send this one to a game 7. Go ahead, 50.
In game 7, is it an ionic compound or is it a covalent compound?
You wasn't supposed to hear that.
So that means you got to answer the question since you talked about game 7. Ionic or covalent?
You said would a game 7 be an ionic or a covalent compound?
No, I'm saying is an ionic, if you gain or lose electrons, or if you're gaining and losing electrons, is that going to be an ionic compound that's formed, or is that going to be a covalent?
If you
or a molecular compound. It's going to be an ionic, that's right. So if you're sharing electrons, then that's going to be
covalent.
Covalent. So what are the 2 different types of covalent bonds? So how many different ways can you share? I guess maybe that should be how I ask the question.
The polar and non-polar, isn't it?
That's right, polar and non-polar. That is correct. Okay, so polar means, are we sharing evenly or unevenly?
Isn't polar evenly?
Nope.
Oh, shit. I always,
Uneven.
Okay, it's 50-50 chance, right? So polar is uneven, right? Non-polar is even. Okay, So we've talked about the number of protons, the number of electrons, the number of neutrons, right? We've talked about the ion itself. So the next thing that I wanted to talk to you about is size of the atom, right? So here's a good example. So we have the sodium atom here, right? This is the sodium ion. Sodium atom basically has 11 protons, 12 neutrons, 11 electrons. Now, the sodium ion has 11 protons, 12 neutrons, and 10 electrons. Now, the size of the ion is going to be smaller than the size of the atom. The reason why it's going to be smaller is because you have more positives in the middle, and it's going to be pulling that one less electron closer to itself. So that positive charge is going to be pulling that electrons closer to its body, okay? So the sodium here, it has equal amounts, so its pull isn't going to be as great because you're not slightly positively charged. So the ion is going to be smaller than the normal atom. You guys see that? Yes, no, maybe? Okay.
Yes.
I see nodding, but verbal commands help me a little bit more because occasionally I see nodding. Okay,
Yes.
so let's talk about the periodic table. Can you guys see the periodic table right now?
Yes.
So,
Yes.
as I go from left to right, my size is going to get smaller. Okay, so the reason it's going to get smaller is because the number of protons are going to be increasing, right? So it's going to have a stronger pull on that the center part of the atom, the nucleus. So the nucleus is going to be pulling those electrons closer to it because there's more positive charge. Okay, so lithium is going to be bigger in size than beryllium. Beryllium is going to be bigger in size than boron. Boron is going to be bigger than size than carbon, right? So it's going to get smaller in this direction. Okay, so the periods are kind of like, even though we haven't talked about it, the Bohr atom, which we will be talking about next chapter. So in the case of the nucleus, we have the nucleus in the center, and then the periods are kind of like adding rings on the outside. So have you guys played with, what are those dolls called? The dolls that fit inside of each other, the Russian dolls that fit inside of each other?
Oh yeah.
Yeah.
Okay, so have you ever played with those before or seen them? Anybody not seen the Russian dolls? Where you have the little doll in the middle, then you have one that's a little bit bigger, then one that's a little bit bigger, and then one that's a little bit bigger? You guys seen that?
Yeah.
Okay, so the periods are kind of like that. So period 1 is kind of like the little doll in the middle. Period 2 is the second size. Period 3 is the third size, and then the fourth size, and then the fifth size. Okay, so the center is going to be your nucleus. On the outside, you're going to have your electrons. Your electrons represents this purple space, right? Or sorry, let me go back to this. So your electrons represents this purple space, right? So, but that purple space is going to be organized in terms of your periods or your energy level. So the first one, your period 1 or 1, that's going to have that first circle. And then period 2 is going to have another circle. And then period 3 is going to have another circle. And period 4, so on and so forth, right? And it's going to change, but for right now, just think of it as a big ball. Big balls instead of dolls. So you have that one ball, and then you have a ball that goes outside of that, and then one that comes outside of that. And so it gets bigger as we go. So in that case, as I said, as we go across, the atom gets smaller. As we go down, what's going to happen?
It gets bigger.
It's going to get bigger. Okay, so the size of the atom is going to get bigger. So looking at the periodic table, these guys here, let me kind of explain this real quick. These guys, they actually fit in this slot right here, right? So the periodic table, what it really looks like, let me show you. Okay, so this is what it really looks like, right? So where your lathoids, your lanthanoids and your actinoids are all, they're located here, okay? So this is what it really looks like. So based upon your periodic table, right, who's going to be the biggest atom? And who's going to be the smallest atom?
Hydrogen?
Dot. And then when you go back, it does that.
Okay, so biggest is going to be who? Did you say hydrogen?
Or is it, I don't know what the FR says at the bottom.
Francium.
Oh, francium?
Yep. So francium is going to be our biggest.
Yeah.
It's going to be big boy. And then who's going to be the smallest?
Okay, so then it would be hydrogen.
Nope.
For the small? No.
The helium?
Helium is going to be the smallest. Okay. Now that makes sense because based upon the fact that you have more positive charge in the center of helium than you have in the case of hydrogen, it's going to be smaller than the hydrogen atom. Okay, but if we're comparing just this group here, then you would say, yeah, hydrogen would be the smallest and francium would be the biggest. Okay, you guys get that?
Just
Yeah.
Yeah.
Here. So we've already talked about how to predict charges, right? Because you know that if it's a group 1 metal, what's going to be the charge if it forms an ion? Plus, right? If it's a group 2 metal, what's going to be the charge?
Negative.
Okay. Group 17, that's your halogens. What's going to be the charge on your halogens? Negative. And then our, halogens, group 16, which is where oxygen is at. What's going to be charged on that?
-2.
-2. Okay. Piece of cake. Not too hard. And so we've gone over this as well, right? So this is just basically giving you an example, specific examples, right? So these are some of the common ions that are observed, right? And so we know that all of these guys are going to be +1. All of these guys are going to be +2. So when we get to the transitional metals, remember I told you they were a hot mess? So these are the common ones. These are the ones that are most commonly seen. So for chromium, we have 3+. We have 6+, but it can also be 2+, right? Manganese, 2+. Iron, 2+, 3+. Cobalt, 2+. Nickel, 2+. Copper, +1. or plus 2. So you can kind of see transitional metals, they don't have, they're a hot mess, right? So there's no consistency to what they are. But in this case, these are just some of the most common charges. And so there are other ones that can exist as well. Okay. And then over here, always -1. These guys, -2. These guys, -3. This one, -4, or it could be +4, depending on who it's working with or interacting with. Okay? Questions?
Nope.
Cash. So, how you feeling so far? Nobody want to
Okay.
jump bridges? Jumping off of bridges? No jumping off of bridges, right? We're good?
No, not yet.
Yeah.
Not yet. Okay, good, good.
I'm
I
not
like hearing
going
that.
crazy yet.
You're not going crazy yet.
Dr. Henry, you said that you would be willing to print out 2 more trees.
Yes, yes, I'll kill a couple of trees for you if you let me know that you're interested. So what do you
'cause
want?
I'm struggling between the last set of notes, flipping back and forth, and following this one. So I'll take
Okay.
a set.
Okay, so you want a complete set of the notes from the whole semester?
Yeah, if possible.
Okay,
Yeah.
okay,
Because I was reading, because when you were going over that last one, I was looking at the electron negativity, and I was looking at the orbitals. So I was jumping back and forth trying to figure out like where we were at. So yeah.
okay. Good, good, good. Let's see. Okay, so our next thing that we're going to talk about is polyatomic ions. Okay, so far we've talked about monatomic ions. Monatomic meaning one atom. So that's like our sodium plus. Ah, shit. That reminds me, I have to put that up for you guys. So you guys will get a sheet of all the polyatomic ions, because I don't really believe in having you guys memorize them. I prefer you know them. And so the way that you know them is by using them. So I'm going to work you like a dog till you learn them. Okay, so a polyatomic ion is ions that have a charge for the entire molecule. So you have usually a covalent molecule that has a charge associated with it. So for instance, we have sulfur or sulfate. Okay, so this is a covalently bonded molecule that has sulfur and 4 oxygens. And it has a -2 charge associated with it. So it has 2 extra electrons. And so since we have 2 extra electrons added to it, it's going to interact with something and form a covalent, an ionic compound with that sodium. With, let's say, if we add sodium. So how many sodiums, which is Na+, could interact with my sulfate to balance it out so that it'll be neutrally charged?
Wouldn't it be 2?
So I would need 2 sodiums to interact with my 1 sulfate. So then when it forms its ionic compound, I would have Na2 SO4. And I would call this sodium sulfate. Okay? So this guy,
Do we cross multiply here or no?
yes, in a sense you can cross multiply, right? Or you could just write out the fact that you need 2, because we know that sodium has a +1 charge.
Yeah.
The sulfur has a -2 charge. How many sodiums will I need to neutralize that? -2 charge. 2.
Yeah.
Okay. So let's say we have calcium, and I have another polyatomic ion called phosphate. Now, phosphate has a -3 charge. Okay, so since phosphate has a -3 charge, how many calciums are going to be able to neutralize this? Now, you're talking about cross multiply. This is a great opportunity to use that concept of cross multiply. So, how many calciums will I need to neutralize my phosphates? And how many phosphates will I need to neutralize my calcium? Here we have +2. This is -3. So in this sense, what was that?
3 calciums, 2 phosphates.
So I'll need 3 calciums and 2 phosphates. Okay. So then my compound, my ionic compound, will be written as Ca3PO4. Now we need 2 of them, so we need 2 of the phosphates, not just 2 of the phosphates. 2 of the phosphates. So we want to put parentheses 2. Are you with me?
Yes.
Okay, so we know what a polyatomic ion is, right? So we also have what we call oxyanions. Oxyanions are polyatomic ions that contain 1 or more oxygen atoms. So these are both examples of oxyanions. Anion meaning negative, so oxygen ion. Essentially, that's what you're telling me. I have an oxygen negatively charged ion, oxyanion. Okay, piece of cake so far?
You said that was a what kind of yeah, okay, that was an oxyanion. Okay.
Oxyanion. Yep.
Got it.
Okay, can I erase? Ready to move on?
Hold on, let me take a picture.
Okay.
I got my starting.
Take a picture.
Okay.
A screenshot.
Okay, you got them? Everybody got their picture? Joe, do you want me to post for you too? Okay. Okay, good. Okay, so now that you've been introduced to it, right? So these are the most commonly used polyatomic ions. You need to be familiar with this. Actually, you need to know them. And I should make you memorize them. But again, the best way of learning them, the best way of memorizing them is by using them. So like I said, I'm going to have you naming compounds after compounds after compounds after compounds until they kind of just seep out of your head. They're just going to be flowing from your head. Okay? So let's talk about a couple of them. Ammonium. You guys heard of ammonia, right?
Yeah, that's the first one that I know.
Ammonia. So ammonia is NH3 with no charge associated with. Ammonium is the polyatomic ion that has that extra hydrogen. Ammonium. So that's NH4 plus. Don't get them confused, right? Very similar. One can form the other, right? Or you'll see reactions where they're formed from one another. But hydronium. Hydronium ion is just water with an extra H plus. Okay, so that's your hydronium ion. Peroxide. So that's O2, 2 minus. So hydroxide is OH minus. Acetate is CH3COO minus. You'll also see it written as C2H3O2 minus. Cyanide, Cn minus. Azide, N3 minus. Carbonate, CO3, 2 minus. Bicarbonate, bicarbonate puts a hydrogen here. This is also called hydrogen carbonate. Both answers will be acceptable. Nitrate is NO3 minus. Nitrite is NO2 minus. So 8 would be what it standardly is. ITE means you're losing 1 oxygen. And if you go hyponitrite, that's going to be NO minus. That means you've lost 2. So hypo meaning under, and then ite means that you lost that 1. So you lost an additional oxygen. Okay. You could also have per nitrate. That means that you gain. So if I tell you your kids are hyper, what does that mean to you?
They're going crazy.
Too much energy.
Too much energy. So it's an extra, right? Extra energy. So in this case, that per means it's what we're using short for hyper, right? So per nitrate means that we have an extra oxygen. Okay. Are you good so far?
Yes.
Okay.
Yes.
So then we have sulfate. So if I wanted per sulfate, how many oxygens would I have? And what would be the chemical formula as a whole? Now, don't all you guys yell at me at once.
Can you repeat the question?
So what would be the chemical formula for per sulfate? So
SO4
sulfate is-
plus.
If sulfate is SO4 2 minus, so what would be per sulfate?
SO4 negative.
Nope. So what is the difference between nitrate and per nitrate?
You're adding.
There's
What?
the difference in the.
Right?
What am I adding? What is the difference between these two?
Yeah. So
Is it SO5?
it would be
That's right. It would be SO5 2 minus.
Wait. Okay.
Okay. So that per means we're adding an
Can you
additional
mute your
oxygen.
TV or turn it down or something, whoever has that background?
not me.
Can you hear me now? Okay, so that per means that we're adding an addition. Okay, are you guys, you got yourself muted? Good. Okay, so that per means that we're going to be adding an additional oxygen, right? from that 8. So if the 8 has 3 in this case, then it goes up to 4. So per sulfate, well, sulfate has 4 oxygens, so we're going to bring it up to 5. So can you guys see that?
Yes.
Okay. So HSO4 minus, that's going to be hydrogen sulfate. Just the fact that we added a hydrogen to it. So this is sulfite, SO3, 2 minus. So if I want to go hyposulfite, what would be the chemical formula for that?
SO4 2 minus.
The
That's right.
SO2. Oh.
You say SO4 or did you say SO2?
It'd be SO2, right?
SO2.
SO2.
Sorry.
SO2, 2 minus.
Minus.
Right?
Yes.
Okay, piece of cake?
Yes.
Okay, so we're going to stop here.